exponential and logarithmic functions. We'll start in 4.1 with what is the exponential function. 4.2 will be what is the logarithmic function. And then in 4.3 and 4.4 we'll start taking the derivatives of these functions. So 4.1, the exponential function, we're going to figure out what that is, look at its graph, talk about the number e. The big applications from this section will be compound interest and logistic growth. So let's look at what are exponential functions. So exponential functions are functions that look like b to the x, where b is a positive number not equal to 1. We say not equal to 1 because if b is equal to 1, then 1 to the x is just 1 for all x, and so that's the boring function that's just the flat line, horizontal line at y equals 1. Anyway, so the exponential function looks like b to the x, something along those lines. Here that number b is called the base. And then properties of exponential functions, they're continuous, the domain is all real numbers, you can plug in anything you want, and the range is all positive numbers. So these functions only spit out positive numbers. The difference between the power function and the exponential function is where that b and the x are, right? So notice in something like x to the b, like x squared, x is the variable, that's at the base. So if the variable is the base, that's just a polynomial. If the base is a constant, so if it's like 2 to the x or 3 to the x, that's the exponential function where your variable x is in the exponent. So be careful with that. When we start taking derivatives, it is not the same as what it is for the power function. So we'll have to be able to identify the difference. With practice, you'll be used to that, and it'll become easy, hopefully. So what do the graphs of these functions look like? So let's look at b to the x, where b is greater than 1. So I picked 2. You can pick your favorite number greater than 1 and graph it. So go to your calculator if you have it with you, or look at it and graph that, see what it looks like. We know it should be continuous, have domain all real numbers, and should spit out all positive numbers for the range. And here's what that looks like. So it is continuous. As you come from the left to the right, we're increasing. So if you ever hear speak a math phrase, exponential growth, but it's a common language as well. To say something is growing exponentially, that's where this comes from. So as you go from the left to the right, it's increasing, and it's increasing faster and faster and faster. Right? So the more to the right you go, the more you're increasing, and the faster you're increasing. As you go to the left for negative x values, you've got a horizontal asymptote at 0, and so to the left, those numbers are getting very, very, very small. To the right, as you go out to positive infinity, it's blowing up to really, really large numbers. And notice I've graphed it there. The point 0.01 is always on that graph. It's because if you plug in x equals 0 for any base, any number to the 0 is 1. So that 0.1 is always on the graph for something like b to the x. So that's what it looks like for b is greater than 1. What if we look at b is greater than 1, but this time it's to the negative x? What does that do? Well, the negative x just flips everything, right? So what used to be the positive side is now the negative side, and what used to be the negative side is now the positive side. So it's the same graph, but it's been flipped around that y-axis. So now this is a decay, right? So as we move to the right, which we always think of as time going on or something like that, we're getting really, really close to 0. So we start really high with these negative numbers, and then we decrease down to 0 as we move to the right. Positive x, but here we're going to choose, instead of b greater than 1, between 0 and 1. What does that look like? Well, that's exactly what we just had. It's a different way to write that. If you choose, let's say, 1/2 to the x, that's the same thing as 2 to the negative x, right? So remember that negative exponent flips your fraction, so the numerator becomes the denominator and vice versa. So this looks exactly like b to the negative x if b was greater than 1. So what I've graphed here is 1/2 to the x, but that's the same as 2 to the negative x, which is what was on the last slide. All right. Next we have the same thing. It's b between 0 and 1, but this time to the negative x. And you can imagine that that's basically flipping it and then flipping it again, where between 0 and 1, we flipped it like what we had on the last slide, but this time throwing that negative x in there flips it back to normal, if that makes any sense. So this looks just like, this is the graph of 1/2 to the negative x, but that's the same thing as 2 to the x. So this is exactly what we started with. So that's, again, growth. As you move to the right, it's going up. Excuse me. We have 2 more here. So what if I throw a constant in front of the x? So instead of just 2 to the x, what if I graph 2 to the 10x? So I've got both of those graphed here. That red one is 2 to the x. The blue one is 2 to the 10x. So it's the same base, but what if you multiply by a number greater than 1 in the exponent? And what that does is you're going to increase faster than you were, right? So this blue graph is 10 to the x. I'm sorry, 2 to the 10x. The red graph is just 2 to the x. So throwing a number greater than 1 next to the x in the exponent means that you're going to grow a lot faster, right? You can think of that as it compresses your graph to that y-axis. It squeezes everything into that y-axis. But let's choose a number less than 1, but a positive number. What that does is that slows the growth down. So that pushes, that red graph is still 2 to the x. I've graphed here 2 to the 1/4 x. So that slows it down. So we're still growing, but instead of growing a lot faster, when we multiply by a number greater than 1, we're going to grow at a slower rate if we multiply by a number between 0 and 1. What you should notice is the closer that number a is to 0, the flatter that graph's going to be, and it's going to get closer and closer to the line y equals 1. And that's because if you plug in an a equals something really close to 0, that's going to just flatten that out to the point where it's almost not growing, but it really still is, and it does still go off to infinity. It just takes a really long time to do that. Anyway, so these graphs, this is just to become familiar with exponential functions. There'll be a couple homework problems on this, but it's really to familiarize yourself with what do these things look like, what are they. We'll talk about why we care about them. But moving forward, you're not going to have to know all of this exactly. It's all about just being familiar with what exponential functions are. That's why we went through this. Okay, let's jump into an application of exponential growth. So we're talking about exponential functions, and you can talk about exponential growth in terms of money, right? Who doesn't like money? And so one thing that deals with that you might have seen in business pre-cal, in fact you should have seen, is called compound interest. And so what that is if you invest P dollars in an account at rate R, it's compounded n times a year. After T years, this is how much you have. It's A of T is P times 1 plus R over N, and that whole thing is raised to the NT power. So if I give you a setup and say, I've invested this much at this rate, it's compounded this time, you just plug everything in and you'll get the amount in the future. One thing to note here is that rate, if I say it's 4%, you got to plug it in as a decimal, 0.04. 12% would be 0.12, etc. So that rate has to go in as a decimal. Okay, let's look at an example of that. So if Tucker invests $100 in an account with 7% interest compounded monthly, we want to know how much will be in the account after 5 years. So let's remind ourselves of that equation. It says the amount after the given time is P times 1 plus R over N to the NT. Right, so the way I like to do these problems is to just make a list of everything I'd like to know. I want to know what is A, I want to know what is P, what is R, what is N, and what is T. Right, well A, let's start at that. What is A? Well, that's what I'm looking for. I don't know. So I'm going to put a question mark. P, that stands for principal. That's the initial amount invested. So if it says Tucker invest $100, that's my principal. So P is 100. My rate says 7%, so to turn that into a decimal, I get 0.07. N, that is the number of times per year that compounding is happening, right? So we're talking about monthly. So since there are 12 months in a year, n is 12. If we were talking about annually, that would just be one time a year, and n would be 1. If we were talking about daily, assuming it's not a leap year, that would be 365 times a year. So n would be 365. So whatever that per year is, that tells you what n is. And lastly, t is the number of years, and so it says after 5 years. So what I'm going to do is plug all of that in. I'll go ahead and let you guys do that, but I won't write it out. When you do that, I got 141, and then I'm going to stop at pennies, so that's 0.76. So after 5 years, that's how much will be in the account. So you make your list, identify everything you know, solve for the thing you don't know. All right, let's move on to the number e. So this e is an irrational number. It's a transcendental number, whatever that means. Don't worry about it. It's like pi, right? So we all know pi is 3.1415926, whatever. E is like that, right? So it's a decimal. It's 2.718 something. Don't worry about it. 2.7-ish. That's all you really should know. And it goes on forever. It never repeats. But it's a really important number, especially in a lot of applications. Let's see where did that random number come from, right? It's defined as the limit as x goes to infinity of 1 plus 1 over x to the x. I don't expect you guys to know how to take that limit. It's not an easy thing to do, but if you trust me, I tell you it's about 2.7, and it's what we call that number e, is that limit. So that's where this comes from. It's really popular in a lot of applications. This shows up. It's just a really good number, right? But it shows up a lot as the base of an exponential, right? So we'll look at things like e to the x. And in fact, that's what we'll be looking at exactly, is e to the x and other things that look like that. So let's look at that. Really, I say e to the x. What I mean by that is a number a, I've written that as a sub 0, a naught to match the book. A sub 0, e to the kx, or maybe negative kx. Those functions that look like that, the one on the left, f of x, that's called growth, and the g of x is decay. Similar to what we've seen before where it was an arbitrary base, but here we've got base e. So these two functions have the following properties. Their domains, all real numbers. You can plug any x you'd like in. The range, again, like before, is all positive numbers. They're continuous and differentiable everywhere. Trust me on the differentiability part. We'll figure out what the derivative is in 4.3, so that's next time. And then the point 0, a naught, a sub 0, is on the graph of both of those guys. That's not, again, this section is all a primer about eventually we want to take these derivatives. So these are just things to have in the back of your mind. It's important to know that these graphs look similar to the ones we had before, and we're going to use them for applications of things. Oops, I forgot. Lastly, like I said, f of x is growth, it's increasing. G of x is decay, it's decreasing. So you should already know then that the derivative of f of x is positive everywhere because it's increasing. The derivative of g of x is negative everywhere because it's decreasing, but we'll talk about those derivatives, like I said, in 4.3. Let's look at an example. It says the function a of t, which is given, is a good model for the amount of bacteria on a table t minutes after they were first on the table. So I say how many bacteria are expected to be on the table after 45 minutes. How do we answer that question? Well, we're going to plug in t equals 45. So let's plug in t equals 45 to answer that first question. I'll let you plug it in, and if you trust me, I got about 1,024. So that's just plugging in, and that's the answer for that. It says, what about after 2 hours? Well, 2 hours is how many minutes? 120, so let's plug 120 in. Again, I'll let you plug it in and check, but I got about 33.5 million. So there you go. That's just plugging things into our exponential functions. Make sure you're comfortable plugging that into your calculator. That's something we'll... Oh man, my picture just jumped out at us here. What is that picture? So that's something called logistic growth. We've been talking about exponential functions, and I've used the word exponential growth. What is logistic growth? You can see over here, it sort of looks like exponential growth, and then over here, it starts looking like exponential decay. So what's happening with that? Well, it's still growth, but what it is it's restricted. So it's going to grow exponentially for a while, and then at some point up here, it's going to start to taper off, and then it has a horizontal asymptote at some level, right? And so eventually that growth is restricted by something, right? And so this, again, is a real-world application. It's used to model a lot of things, but this growth type of logistic growth always looks like the exact same function that's given here. So you have a capital M, and which is a variable. A is another variable, and then we have a K. T is, I'm sorry, those are constants, not variables. M, A, and K are all constants. T is our only variable. So we're plugging in T and spitting out whatever height we're at. It's important that all these, the M, A, and K are all positive. And this M is important. I've boxed it. That's this height where we have this horizontal asymptote. That's our limit, right? If we plug in T is larger and larger and larger, this whole term down here starts to go away, right? So we end up with something that looks like M over 1 plus a really, really, really small number. So that's, when we take a limit, the same as just M over 1. So if we take the limit as T goes to infinity, we just get M. So your book will use the word max for that. It's not a true maximum, but we'll use the word max. If I give you this function and say, what does it look like in the long run? You just know it's the numerator. You don't have to show work for that. You just say, I know what this function looks like, and it's just going to be the numerator. So I give you this function. So first off, you have to recognize that looks like a logistic growth function. It's a number divided by 1 plus something that looks like exponential decay, right? So with that negative KT. So that says if this models the number of car sales per year, where T equals 0 is 2010, I'm asking how many cars were sold in 2010. So what we're going to do, since T equals 0 corresponds to 2010, we're going to plug in 0. And I'll let you guys check that, but I got 24,761. So that's from plugging in 0. All right, and then it says how many were sold in 2015. So if T equals 0 is 2010, 2015 is T equals 5. So let's plug in 5 and double check me, of course, but I got 142,196. I've rounded these to whole numbers because we're talking about cars, which you can't sell half a car. I don't know, maybe you could. That doesn't make much sense. So I've rounded them to whole numbers. All right, so now is where we get that logistic growth. If it holds forever, so that keyword forever makes you think we're going to take T going to infinity. Whoops. Sorry about that. So we're going to take T going to infinity. That's what that forever thing should tell us. And then it says at what level will it stabilize? So that sort of makes you think, okay, it's leveling off, there's a maximum, whatever. That sentence, if the model holds forever, at what level will it stabilize? That's where you say, this is logistic growth. I know that that's the numerator. So the answer for there, you don't have to say anything other than it's the numerator, and then box that. Well, and that's the end of chapter 4. So it was really an introduction to exponential functions, and messing around with them, seeing what they look like. You should do these problems. They're good practice. I think I've only deleted one from the homework list. But the key things here are you have to memorize the equation for compound interest. You have to memorize that. And you have to be able to recognize that logistic growth and know that if you're talking about in the long run or whatever, that is going to be just the numerator. And of course, the other thing we did, we just plugged things into exponential functions. So you need to be comfortable with that as well. On to 4.2, the natural logarithm function. So we're going to introduce that, say what it is, where it came from, we'll talk about converting exponentials rather, to logs and vice versa. We'll look at the properties of these logarithms and talk about solving these logarithmic and exponential equations. Ideally, this is all something you saw in business pre-cal. You should have seen all of this already, so this should be just a refresher. But if it's not so much, or if you totally forgot all that since then, that's quite all right. So let's start with what is the natural logarithm function. What it really is logarithms are exponents, right? So if a is e to the t, then t is the natural logarithm of a. So the natural logarithm of a is the number that goes in the exponent of the e to get what is equal to a. So let me say that another way. The natural log of a is the thing that goes in the exponent of e, so that e to that is equal to a. The formal definition of that, we use this little ln for the natural log. So the natural log of a, that's what this says, equals t if a is e to the t. Right? So that's what I said in a different way. This is hopefully a little bit more clear. The natural log of a equals t if a is e to the t. All right, so we know that from 4.1, e to the t is a positive number. That was the range of those exponential functions are always positive. Then, because of that, if a is e to the t, a is always positive. That means that the only thing you're allowed to plug into these natural log functions is positive numbers. So you can't have natural log of 0, and you can't have natural log of negative numbers. You can only plug in positive numbers. So of course this is a function, natural log. So we can say y is natural log of x, or natural log of 2x plus 1. Eventually the goal is to start looking at the derivative of things like this. That'll come at the end of chapter 4. An example, it says convert the following logarithmic equations to exponential ones. So this is just using our rule. So 2 is natural log of 6x. That means that e to the 2 is 6x. Right, so the way I always think of this is like there's a little base e. Right, you remember in pre-cal you should have seen things like log base a of b, things like that. So this is log base e. So what you want to do is switch that, and since it's base e and base a, it's the same thing where the base of the logarithm, which was an e, becomes the base of the exponent, and then you flip the other two. So you drop down your base. This is how I think of this. You drop down the base, and then you flip these two things here. So you get 6x is e to the 2. However you want to think about that. If you just want to memorize, taking it to there. If you like this method over here, that's fine too. Another thing you can do is we know that if 2 is natural log of 6x, then e to the 2 is the same thing as e to the natural log of 6x. And this e and the natural log on the right side over here cancel each other out. So that says that e squared is 6x. However you want to get there, those are all three perfectly fine ways to do that. Let's see how we would do it in this next one. So I like to do this one I've circled. So I'm going to drop down my e, and then what was on the left, I'm now going to put in the exponent. So that's e to the x plus 1. And what was inside the log is now by itself. So this is y minus 3. And I'll let you guys do number 3 here on your own. Pause the video, try it just a second, write it down real quick. You can probably do it without pausing because I'm going to ramble and allow you time. All right, so let's say you've done that. Then what do you get? You drop down your base e, and then you get to the negative 3. And what was inside the log is now by itself, so x plus 5. So there you go. Here we're going to go in the other direction. So we want to say convert the exponential equations to logarithmic ones. So here's an exponential equation. We want to turn it into one that has a log instead. So there's a few ways to do this, just like before. One way you could think is, what if I just do the natural log of the left side and the natural log of the right side? That'll still be equal. But again, this natural log and e cancel each other out, and you get 3x is the natural log of 2. You could also just think that, remember, by definition, the way we said that, the natural log of 2 is exactly what goes in this exponent. So you just think the natural log of 2 is 3x and take straight from there to there. That's okay too, however you want to do that. So what about this? What's e to the x plus y equals 2y? So that's going to be the natural log of 2y. Again, I'll let you justify this by looking back at the notes if you have to. But the natural log of 2y is the thing in the exponent of the e, which is x plus y. All right, same thing here. You'll get the natural log of 2x minus 1. Well, that's what goes in the exponent of the e to make these things equal. So that's exactly minus 3 plus x. All right, what is the natural log of e? The natural log of e, if I say I don't know what that is, call it x, by what we were just doing, what this means is that e from the base, and then I switch, so e to the x is e. Well, that happens if x is 1, right? E to the what is it e? That means you didn't change it, so x is 1. So the natural log of e is 1. And again, that's the e and the natural log are inverses. They undo each other. What about the natural log of 1? So the natural log of, whoops. Sorry about that. The natural log of 1, if I say I don't know what that is, let's call it x. That means that e to the x equals 1. Well, what number goes in the exponent to say e to the blank is 1? Well, that's anything to the 0 is 1. So x equals 0. So those two things are going to be the first properties of logarithms, that the natural log of e is 1 and the natural log of 1 is 0. We also have that the natural log of e to the x is x, and so that's where you can think of natural log and e undoing each other. They're inverses. And we have here that the natural log of xy is the natural log of x plus the natural log of y. So if you're multiplying on the inside, you can break that up and make that addition. That should be semi-familiar to you, hopefully, especially if you think of, remember, these natural logs, these logarithms are exponents. And there's an exponent rule where if you have e to the x times e to the y, so again, that's multiplication, well, that becomes addition. So in the exponent, that's e to the x plus y. That's the same thing that's going on over here. If you multiply, that becomes addition. And so that's where that comes from. And the same scenario, remember, we have e to the x over e to the y, or any other base. It doesn't have to be an e, any exponent. That's e to the x minus y. Those are just exponent rules that you should know. And that's where this comes from. If you're dividing, it becomes subtraction. And the last thing we have is that the natural log of x to the r is r times the natural log of x. So that's just where you can pull out an r to the front. And that comes from something like e to the x, you raise a power to a power, right? If you have an exponent raised to a power, then that becomes multiplication. So that's the parallel to that rule for logarithms. So if it looks like x to the r, you can pull the r. I gave you this logarithmic expression. I want you to use all of your properties of logarithms to expand this thing out so that it looks like a logarithmic expression that has all the variables have just an exponent of 1. Right, so this is really just a way to practice using these logarithm rules. So what does that look like? Well, since we're dividing, we can break that up using our rules into subtraction. So that's the natural log of 2x cubed minus the natural log of y squared z. Right, so since we were dividing on the inside of the log, we made that a subtraction of the two logs. Now in both of these logs we're multiplying. We have a 2 times x cubed and a y squared times z. So we can break those up into two different sums. So this part right here is going to become this, the natural log of 2. And then since we multiplied by x cubed, we're going to add the natural log of x cubed. So that was that part. And then this part right here, we're going to subtract. So we have the natural log of it's y squared times z. So we're going to get y squared plus the natural log of z. And now the last thing to do is to get these exponents to be 1. So what we're going to do there is use that property of pulling the exponent out to the front. So when we do this, that natural log of 2 is fine as is. And then since it's an x cubed on the inside of the natural log, we can pull that 3 out into the front, and you get 3 natural log of x. And then we're going to do the same thing with this y squared. It's going to bring us a 2 in the front. So that's 2 natural log of y. And then don't forget to distribute this negative sign right there. So we get a negative minus natural log of z. All right, and that's just practice using these properties of logarithms. I'll let you guys do this one on your own. So we're going to go backwards, and the goal is to use all these properties of logarithms to get to the natural log of and only one thing, right? So you guys try that one on your own, but what you end up getting is x times z to the 10 over y squared. But I'll let you try that on your own. Make sure you can get that. You're just combining. So as your hint, you can start with turning this into division, and then whatever you get from that plus this piece you can do multiplication with. Before you do the division, you'll have to pull these 2's up here, the 2 and the 10, into these exponents. So I've pretty much done it for you. You can fill in the gaps and get to this thing here if you'd like. Okay, so now we've been given an exponential equation and we're asked to solve it. So the way we're going to solve these exponential equations is to write them with logarithms. So our first step is we want to get to something where we have e to the stuff equals whatever. Once we do that, we know that the log, the natural log of the whatever, equals the stuff, right? So our goal is to make it look like this, and then substitute in, change it to logs. So in order to do that, we need to get rid of this 4. So divide by 4, you get e to the 3x minus 1, and 12 over 4 is 3. And hey, now this looks like that. So we can turn it into something that looks like this using the natural log. So what that says is that 3x minus 1 is the natural log of 3. And now we're actually able to solve for x where we weren't able to before because it was in the exponent. So if you add 1 over plus 1 and then divide by 3, you get x is the natural log of 3 plus 1 over 3. And that's it. You can just leave it like that. Don't make that a decimal number. Just leave it as natural log of 3. All we're doing in 4.2, this is really just a big setup into us taking derivatives of things with logarithms. But it's good to refresh ourselves on what these things are and to remind ourselves of their properties. I've left the homework list as is. Just make sure that you are comfortable with logarithms and converting from logarithms to exponents and solving those equations. You don't need to do the whole list unless you feel like you really need that practice. And there's Penny. All right, bye-bye.